Hello and welcome to Critical Thinking Lecture 8. Today we're going to be talking about properties and relations and properties of relations. Starting here, properties. Look, we refer to objects in the world directly or indirectly, among other ways. If I point to Sam and I say, "There's Sam," I'm referring to Sam directly. If I gesture in his direction and say, "That person over there with a blue hat and red shoes," I'm indirectly referring to Sam, and that's the distinction. Now, when we refer to individuals and objects indirectly, we often describe them using properties they have. For example, by referring to Sam as wearing a hat, I'm describing Sam as bearing the property wearing a hat. I'm going to use italics to indicate that I'm talking about properties in many cases. Hopefully context will decide. Now, properties, generally speaking, are everywhere. Here's an example of a thing in the world. I'm sure you've seen one. If not, it's an apple. It's red. It has that property. It's also round, it has that property, and just for fun, it's an image, because you're not actually looking at an apple, you're looking at something on a screen, ha ha ha. But in any event, this screen, or this picture here, is an image. It has the property of being so. Now, some natural language properties link to other properties. For example, if an apple is red, then the apple has a color, and those are both properties. Now, if an apple is round, it also has a shape. Again, properties. And of course, if an apple is an image, then it represents something. Representing something can be a property as well. Now, identifying these relationships may help you learn a lot of info about things just based on a little. So, I'll illustrate. Suppose you're playing the game Clue. You know at least one person has committed a murder, but not which. You uncover properties while playing that, when combined, narrow down the culprits. And this is it's a more complicated version of determining entailments based on properties and how they combine more specifically. Now, we can infer information about the world not just based on properties or entailments associated with them, but also relationships between things. Two-place properties, you might call them. Now, here's some examples. John is taller than Sam. Taller than is a relation between John and Sam. Here is the two culprits. There's Sam. Here's John. And here's the relation. Here's how I will represent it as well with this sort of arrow notation. This is going to be taller than. And note this. Note the asymmetry. It's directed, right? John is, follow the arrow, taller than Sam. Sam is, on the other hand, next to John. Also, Sam is smarter than John, and John is heavier than Sam. Sam is the smartest person in the room. Note there are only two people in here. In this case, of course, we're excluding Sam himself because no one's smarter than themselves. Now, relations themselves have properties in natural language, and that can reveal lots of information as well. So consider John next to Sam means that Sam is next to John. Again, here we go. These arrows go both ways. If you have one, you know you have the other. Similarly, John taller than Sam and Sam taller than Sally means John is taller than Sally. Here we go. The culprits lined up, and the relationships borne out with these green arrows, taller than. Now, Sam is the smartest person in the room means Sam is smarter than anyone in the room, of course, excluding Sam himself. Here we have the culprits and the relationships borne out again by these green arrows. Now, we learn a lot. Like you can, in a sense, classify relations based on the properties they have, and several properties are common enough that it's worth naming them. We'll walk through some of these here. So, some properties like I'm going to introduce some notation here just to simplify the discussion. Lowercase letters from the beginning of the alphabet are going to reflect individuals like John and Sam, and uppercase letters are going to reflect properties and relations. And I'll use X, Y, and Z just like you would see in an algebra class to represent variables. So for example, to say John is happy, I'll just write H, lowercase j. John is taller than Sam, I'll just write uppercase T, lowercase j, lowercase s. And to write everyone is happier than Sam, I'll write uppercase H, lowercase x, and lowercase s. Now, we'll say a relation is reflexive, just in case for anything it might apply to, that thing is related to itself. For example, identity is reflexive. This is because everything is identical to itself, trivially. And we'll write x equals x. Now, we'll try this one out. Symmetry. A relation is symmetric. Just in case if one thing is related to another, the reverse relation holds as well. We've already seen this as a matter of fact. The relation next to is symmetric. If x is next to y, then y is next to x. Let next to be represented by this uppercase n, and we'll have if in xy, then in yx. Now, some natural language relations have more than one property. Identity is just that sort of, or just one of those, identity is an example of such. It's both symmetric and reflexive. That is to say, if x is identical to y, and y is identical to x, and x is identical to x, and then that is, if x is identical to y, then y is identical to x, and as a matter of fact, x is identical to itself, and so is y. Now, maybe a slightly more complicated property of relations is transitivity. Relation is transitive just in case if an object is related to another, which itself is related to a third, then the first is also related to the third. For example, the relation is taller than is transitive. If x is taller than y and y is taller than z, then x is taller than z. You can see this simplified notation here representing that. Now, the relation is identical to is also transitive. That is, it's reflexive, symmetric, and transitive. Any relation that has all three of these properties, we're going to call an equivalence relation. And spotting equivalence relations allows you to group things in a rather coarse-grained manner. For example, consider the relation has the same father as. Now, suppose there are several people who bear this relationship to each other. If x has the same father as y, of course, y has the same father as x. And anyone in this group has the same father as themselves, and I'll let you think through the transitivity aspect, but I think you'll agree with me that anybody bearing this relationship will hold, or that property will hold as well of them. Now, I want to give you a simple task to think through some of these. Consider the relation part of. We'll denote it with P. For example, to say that John's elbow is part of John, we'll just write P lowercase ej. Which of the following do you think are true with parthood? Look, everything is part of itself, the maximal part. Consider just John's leg. Now combine this with John's torso, elbow, just sum them all together until you have all of John's proper parts. What's the result? Well, it's John. That might make you think, I think it does, that parthood is reflexive. Now consider symmetry. It seems intuitive to say that part of is not symmetric, right? So to say that something's part of something else often implies that the second thing is not part of the first. We might capture this by saying if pxy, then it's not the case that pyx. Well, I'm going to explain to you why this can't work, given what we've just said a minute ago. Suppose pxy, then it's not the case that pyx. Note the x and the y, they're variables that can be anything in our domain. They're unrestricted. But that means whatever is being picked out by x might be the same thing as whatever is being picked out by y. So we can replace pxy with pxx. And remember, parthood is reflexive, so this pxx always holds. But that means that our supposition we have, if px entails that if pxx, then it's not the case that pxx. But that's crazy. So we have to take back what we supposed. Still, we don't want to say that part of is symmetric. That's also crazy. We get around this by introducing another property of relations. We'll call it antisymmetry or antisymmetric. It's just like this. If pxy and pyx, then x and y are the same thing. And this is consistent with reflexivity because it's weaker than saying what we said a minute ago about not being symmetric. It still gets the result we're after. Now, I also want to introduce you to Leibniz's law. We've seen this before, but here more formally. If x equals y, then any property x has, y has as well. This also applies to properties of relations. We've said part of is reflexive antisymmetric and intransitive as well. I'll let you think through that. Now, let me ask you this. Is the relation is contained in the same relation as is part of? And think about Leibniz's law to answer this question. I'll pause the video and ponder, assuming you've done that. Think about whether is contained in is transitive, antisymmetric, or reflexive. In particular, think about whether it's reflexive. Remember, we just said part of is reflexive. Now, is contained in is not reflexive. Right? It doesn't make sense to say it is, but note, because part of is that, and if we assume Leibniz's law applies to properties of relations, as we are, that's sufficient to show that is contained in is not the same relation as is part of.